Hey everybody, this is Larry. This is I forgot to press the button. Day 2 of the Leetcode Daily Challenge for February. Hit the like button, hit the subscribe button, join me on Discord. Let me know what you think about today's problem. Hope everyone's doing well. It's only the second day, so I hope you're still keeping to this. This is a short month, so hopefully, you get to finish that month, get all those points, get all those coins or whatever, get that t-shirt or whatever. Yeah. Okay, today's problem is trim a binary search tree. So, okay, given a root and a tree, element and trimming the tree should not change the relative structure. It can be proved that there will be a unique answer. Okay. This is going to be a mess. I don't know. Generally, to be honest, I all these binary search tree operations are always going to be a little bit messy, but okay. So basically, we want to get rid of elements that are not in that case. Okay. What do I make of that? I mean, the short answer is still going to be some depth for, or you could do it in a number of ways, but I would probably do it some sort of post-order traversal, but it's just about going through all the cases, to be honest. Yeah. And yeah, I mean, I think this is really, I don't know that there's anything really tricky about this problem per se. In terms of algorithm, I'm thinking about it. For me, it would involve just going through a paper and making sure that everything is that I get all the tests or all the edge cases right. And to be honest, yeah, that's probably going to be it. But yeah, and you have to look at every node because it's not a full tree or anything like that. But and there might be a case where you remove all the nodes, so and changing the root, for example. So yeah. Okay, so yeah, how I'm just thinking about how to explain this one as well. Because I think the thing is that I might actually just think about different visualizations. But what's left of 0, right? Okay. I see why. Because the case that I'm thinking about, and maybe I'll pull out, I don't usually do this because it takes a lot of time, but let me pull out my my paintbrush. Oops. So yeah, so my thought immediately when I saw this is that, like, let's say I have some nodes, like, and I'm getting rid of, we have some nodes, we have some whatever, some tree, something like that, right? Let's say we're getting rid of both. We're getting rid of this node, and we want to keep both left. Oops, both left and right. But actually, by definition, that cannot happen because of the invariant that's in the problem. And the invariant is that you want to keep the things in between, right? And if you want, so that means that if you remove the root node, which is here, let me change the color a little bit. If you get rid of the root node for any subtree, so I'm just like generalizing. So if we get rid of the root node, that means that you have to get rid of, you're only keeping one side of the, like some kind of boundary, right? And from that, so either you get rid of all of the left side or all of the right side, because that's how keeping, because another way to think about it is, let me change the color again. You're either keeping, if you're getting rid of the root node, that means that you're either keeping all of the left or the right, and there's no way to do both of them, because if you want to keep both of them, then you have to keep the bang, you have to keep the root. So okay, so I think from that, I think this problem gets a little bit easier in terms of implementation. So let's get to that then. But that's basically the invariant that I would think about. Though again, I think I just am a little bit lazy with respect to these binary search tree things. But okay. Okay, so let's see. If, and we can just call it directly, I think, maybe. Like we don't need a helper. Let's just use a helper so that I don't have to get confused. So okay, let's just do do we want pre-order or post-order? I think we could do pre-order. I think that's good. A node, and we'll use the left right there, and of course we'll kick it off by calling on the root, and then we just return. Okay, I think what I want to do is actually I have a fake node on. Do I? Because I'm trying to think about a case where if we get rid of the root, right? So and maybe there are other ways to do it, but I'm going to create a standard node. So let's say fake root is equal to this is equal to some really small number, so that is always to the left of everything. So then when we put the node fake root dot right is equal to root, right? And then now we could just do a pre-order on fake root, knowing that we will not remove the fake root, and then now we just return fake root dot right, right? Okay, and then now here, okay, if node is none, we just return, I suppose. I always write that. I don't even know if this comes into play, but okay. So now we check whether we keep root, right? If root dot value is between low and left and right, then we're good. If we're good, what does that mean, right? That means that we could just do a pre-order traversal as well. I think in theory we can probably determine which side to go to do a recursion on, but I'm just going to do both for now. I don't think it doesn't change the oh, and this is no dot value. It doesn't change it too much. So if you want to optimize, you can optimize it, but it's still going to be linear in the worst case. That's why. Else we have to remove this node. So then now we have to check whether, well, in this case, then let's also do pre-order node dot left, pre-order node dot right, maybe. And in theory, I think it just depends on how you want to define the interface, because ideally this would set the node dot left to none or something like that, but maybe that's just silly. So okay, so maybe we can just check if promote either the left or the right, because we have to promote one of them. Let's see. Maybe I'm just trying to too hard to make it not make it cool, but it's not none, and node dot left is low. If this is the case, then we promote node dot it should be something like node is equal to node dot left. But I think that maybe I messed up how I construct this. Actually, give me a second. Yeah, this is messy to kind of keep track of all the nodes. So actually what I want to do is actually do this and then do, so now we keep track of his parent, so then so that's a little bit easier, and then just do fake root dot right, which is the actual root. So then now we have parent and node. Yeah, okay, so if node is none, we return. Otherwise, if this is inside, that's good. We just do a recursion. Otherwise the parent dot, oh, we don't even know which direction the parent would need to change. So, man, there's a lot of like weird things about this one. Maybe there's a I mean, there's probably an easier way, but all right, I'm just gonna do right so that I know as well. So what's it called? Child or something like that. I don't know. If child is equal to left, then parent dot left is equal to node dot left, else parent dot right, or sorry, parent dot left is equal to node dot right. Otherwise, we do the same thing. Oh, wait, no, this is wrong. Whoops, my bad. Yeah, okay. That now. Otherwise, we want to take the parent. Oops. Keep on doing that. Node dot right, else parent dot right is equal to node dot right, because we want to take the right node. And here we will just do a pre-order, and then we do a recursion on that. That should be pretty okay. And then but now we clearly we have to change this. So yeah, node left, node right, and I would also obviously say that this is not the best code, but you know, we'll see. So like, but this is how I would solve it if I saw it in a contest or something like that. So definitely, you know, check that out. Low and high. Oh no, did I make the same mistake in multiple places? I guess so. Where's because I usually do left and right. That's why. Let me also, in the meanwhile, copy and paste this. They need a button for me to run all the test cases. That looks good actually. So, but that's a relatively easy test case. So let's try the other ones. Okay. Oh, that looks good as well. I mean, I would say this is one of those ones where I call it bookkeeping, and it just means keeping track of a lot of things. So as long as you keep track of enough things is okay. There might be a cleaner way to do it, obviously, but and maybe we'll go over some of, to see to go over it. But I'm not, I think this is, unless I'm missing an edge case or a typo, I think this should be okay. And yeah, let's give it a submit, unless I'm missing the no case or something. Oh, I have to check where I removed the root. Yeah, I forgot to check that actually. I knew that I needed to check that, but I forgot. Though I don't know what this error is about. Oh, I forgot that this has visualization. So this is the thing, and you remove the, yeah, as I was saying, like we do not remove the node as a result. Yeah, we do not remove like we don't have a case where we remove the root. So this is wrong, but less than equal not supposed to instance of int and tree node. Int and tree node. Why is this int and tree node? So all these are ints and node dot left. Oh, I just have wow, this never got a that's surprising that I mean that actually turned out to be just a typo, but also just one that somehow never got caught here. Okay, let's give it a submit again. I wouldn't be surprised if I have another wrong answer. Yep. Just mostly because I'm lazy to do this, but okay. So let's visualize this. Oh, there's a visualize button. I click on the button and it doesn't show. Okay, 2, 3, 4 again. Nope, this is this one. Okay, and then now we want to keep 3 and 4. So that seems pretty straightforward. What do I return? I return the one with a 2. Why did I return 2? Okay, it's because yeah, I guess I should have done. I was wrong about the pre-order. I think my original concept was a little bit different than what I end up implementing, so the pre-order doesn't make sense. So we actually need a post order. so that we don't bubble up things that we remove, which in this case we kind of do. Yeah, see, there you go. And you know, you may ask, how did I realize that quickly? It's just because when I saw this, when I saw this, I knew that the 2 was getting bubbled up without like recursive check. So yeah, so let's give it a submit again. Oh no. Oh, okay. So this is actually, I also thought about this case, or actually no, I thought there would be a nothing case, but that's actually odd. Maybe I just have a typo. But yeah, there's a lot of, that's why I was relishing this problem, or the opposite of it, that because I knew that there's a lot of weird cases as such. Okay, this one I didn't expect actually. So you have 3, 2, 4. You know, you bubble up the 1. So what I would, for debugging, what I would do is I want to visualize it every step of the way, but it just may be that some visualization is wrong. I think what I did was wrong in that I know what I'm doing is wrong, is that if this is not true by default, I go to the right side, but that's actually not what should have happened. What I should do is actually, I think when I converted to pre-order post-order, I didn't do that. So then now we can check it afterwards, because we need to check the bubbled up value instead of the value that was before it was bubbled up. Yeah, there you go. I think when I changed it from post-order, when I changed it from pre-order to post-order, I didn't change it clearly. So yeah, okay, there you go, accepted. And of course, there's actually, it turns out that you can, you know, remove some duplicate code. For example, you know, we could probably take this out, and then now, you know, yeah, if not this, I guess. Because that means that we have to do something about this current node, and this is actually the cleaner version of the code that I would like. There probably is still cleaner solution, because I just like to kind of keep the pointer and figure it out. But okay, so what is the complexity of this? This is going to be linear time, because we just do a post order of the entire tree. Space complexity, well, we do keep, you know, stack an implicit core stack. So that's going to be O of h, where h is the height of the tree, O of n in the worst case, where n is the number of nodes. But yeah, I want to say that's all I have. Yeah, it's an annoying problem. It's tricky. Like I said, I think if it was me being more deliberate on a contest or something, especially with a penalty, I'm going to be a little bit more careful and kind of draw out all these test cases. So definitely when you're practicing at home, make sure you get all the test cases or edge cases, because that's the number one concern I have with this, is just getting all the edge cases right. But yeah, that's all I have, I think. Let me know what you think about this code. It's a little bit, I mean, I'm not super happy about it initially, but I think I'm okay with it. I think there's some refactoring you can do with respect to this chunk. If you want to use like Lambda functions or something like that, I think you can actually do something to reduce how it looks. But for the most part, for readability, I think this is okay. Yeah. Okay. So that's all I have. You know, it's at least in New York here, it's cold, so definitely stay safe, stay warm, and if you're already in a warm place, then I don't know, stay at the temperature that you like. But yeah, just, you know, take care of yourself. Remember, this is a long journey. Pace yourself so that you don't kind of get tired and sick of these things. And even like for a problem like this one is a little bit annoying, right? But yeah, take care of yourself, and if you're doing well, then take care of people around you, or even people not around you. And yeah, I hope everyone do okay, do well, to good mental health, and I will see y'all later. Bye bye.